Good morning. Today we're going to talk about linkage and chromosome mapping. We will look at 2-point mapping, 3-point mapping, and reverse mapping. Let's start with 2-point mapping. 2-point mapping implies that we're looking at two genes, i.e. 2 points. So here we have a situation in petunias. Let's get that light on. It's a little better. Where purple flowers are dominant to white and long stems are dominant to short. So at the end of the day, we're going to want to make a map that has the color locus and the stem locus. And we'll get the distance between those. Let's look at the cross. Pure-breeding plants with white flowers and long stems were mated to pure-breeding plants with purple flowers and short stems. So let's see. White flowers is recessive, long stem is dominant. Assuming these genes are linked, we can write that genotype as little p, big L, big L. And that was mated to a plant with purple flowers and short stems. Purple is dominant, short is recessive. So again, assuming the genes are linked, we would write that as big P, little l on one chromosome, big P, little l on the other. Our F1 get one chromosome from each parent. And then those F1 are test crossed by mating them to the homozygous recessive. So this is our genotype of the F1. The phenotype will be the two dominant traits. So up here, purple are dominant and long stem are dominant. The phenotype of the test cross parent is going to be the recessive trait, so white and short. In order to determine the map distance is the percent of recombinant progeny. So we want to look at which of these types are parental and which are recombinant. Our pure breeding parents were white and long, so white and long is parental. And the other one is purple short. So purple short is also parental. That means these last two must be the recombinant. We can calculate the map distance as the number of recombinants. Let's see, there were 75 plus 87 divided by the total number. Let's see, our total here is 752. And that's our recombination frequency. But to get that into percent, we have to multiply times 100. And that equals 21.54 centimorgans. And now we have our map. Okay, this is 2 points. Let's look at a 3-point map. 3-point maps are a little bit more complex because, hey, we got 3 genes instead of 2. So in this case, again, we're told what's dominant and what's recessive, but we're looking at 3 genes in sheep. And this time we're actually given the map. We see that there are 17 centimorgans between the hair type and the color locus, and only 6 centimorgans between the color locus and the horn locus, meaning color is in the center. Here we're going to look at 4 types of progeny from a test cross and try to determine their relative frequency. Well, let's think about this just a little bit. We could have no crossing over anywhere. That's always the most common. We could have a cross only in this first region. That would be an SC1. We could have a cross only in the second region. That's an SC2. Or we could have a double crossover, meaning we got a cross in both regions 1 and 2. So our frequency is always the non-crossover is the most common. The single crossovers are in the middle, and the double crossover is the rarest. We determine which single crossover is the most common by looking at the map distance. The region with the bigger map distance is more common. So region 1 has a map distance of 17. That's more common than region 2's. So SC1 is more common than SC2 with this map. Now, how do we figure out which of these are non-crossovers, SC1s, SC2s, and doubles? Well, let's take a look at that. We need to look at the specific cross. Hairy white sheep with straight horns mated to woolly black sheep with curly horns. We don't care what's dominant and recessive. We put one pure breeding type above the line and the other below the line. So let's see, I've got hairy, white and straight. It does not matter which pure breeding type we put on top and which pure breeding type we put on the bottom. Mated to woolly, black, and curly. Now let's classify each of these types based on whether they are a non-crossover, SC1, SC2, or double, and then we can rank them 1 through 4. Hairy, black, curly. Hairy, start at the top, cross here for black, stay down for curly. That's an SC1. Woolly, black, curly. Woolly, start at the bottom, black, stay down, curly, stay down. NCO, that one's going to be the most common. Let's see, woolly, white, curly. Woolly, cross up to white, cross back down to curly, that's a DCO. That will be the rarest. And hairy, white, curly. So here we stay up in the first region, cross in the second, SC2. So looking at our rankings, NCO is the most common, SC1 second, SC2 third, and double crossover fourth. Remember, non-crossover is always the most, double crossover is always the least. The single crossovers are in the middle, and their relative frequencies depend on the map distance. Bigger map distance is more crossing over. Let's move on to a 3-point map where we have to construct a map. So in this problem, we're starting off with 3 traits in peanuts: flower color, spreading growth habit, and leaf type. And we've got our pure breeding plants that have mated together, and we've got our F1 and test cross the F1. These are the test cross progeny. Our first question was, what is the phenotype of the F1? The F1 show whatever's dominant. So yellow is dominant, spreading is dominant, and pointed is dominant. So they will be yellow, spreading, and pointed. What is the genotype of the F1 indicating the linkage relationship? So remember how I wrote the genotypes on that very first problem with a chromosome from one parent on top, a chromosome from the other on the bottom? That's what we're doing here. So we have to look at the pure breeding type. Spreading, yellow, round would be one. So spreading is a big E, yellow is a big O, and round is a little r. So I've got a big O, a little r, and a big E. And I'm just putting these in random order right here, just how I could think to write them. And the other was erect, orange, pointed. So orange is going to be a little O, and erect was a little E, and pointed was a big R. Once I write the order on the top, I do want the same order on the bottom. The phenotype of the test cross parent is all the recessive, so orange, erect, and round. We know that this has to be exactly opposite of the phenotype of the F1. Now we need to do a chi-square test to determine if these genes are even linked. And it's really appropriate to do a chi-square test for independent assortment before we do any sort of mapping. If we have linked genes, they should violate independent assortment in a chi-square test. We can only test 2 genes at a time. So we could do 3 chi-square tests: color and growth habit, color and leaf shape, and growth habit and leaf shape. We're just going to do one here. Our null hypothesis is always that those 2 genes we're testing assort independently. So the color and leaf shape loci in peanuts assort independently. So our classes: observed, expected, O minus E, and then this is O minus E squared divided by E. And we always have the total. I did total these up, and the total is 1,308. Our classes here are parental and recombinant. Parental, no cross between the color and leaf shape genes, since those are the 2 we're testing. Recombinant, there was a cross. So how do we decide what is parental and what is recombinant? We look at the genes for color and leaf shape. So color, we started off with yellow and round for leaf shape in this non-crossover. So yellow is a big O, and round is a little r. So every time I have yellow and round, that's going to be parental. Yellow round, orange pointed, that won't be it. Let's see, yellow erect, yellow spreading, there should be 4. Ah, of course, that's one of them. We have to look for the other 2. So yellow round, and the other purebred was orange pointed. So we do need all the orange pointeds. So parental orange pointed and parental orange pointed. Notice when we did this, the non-crossovers were parental. That makes sense because we didn't have any cross there. And then this configuration we have for the non-crossovers, so the yellow round and the orange pointed, are the ones that are going to be parental for this particular case. If I add those 4 types together, 461, 85, 450, and 73, I have 1,069. And then I need to find the recombinants. That's everything else. So 11 plus 102 plus 7 plus 119 is 239. And I'm just going to write these here. So the parental was 461 plus 450 plus 85 and 73. And the recombinant was 11, 102, 7, and 119. Just so that it's easier to go back and work through that if you want to. This was a test cross. If we did not have linked genes, in other words, if those genes assort independently, we expect half to be parental and half to be recombinant. So of our 1,308, half of that is 654. I do the math. and my calculated chi-square value was 526.68. It's a really big value. Well, we analyze this the same way you would do the chi-square test we've done before. Our degrees of freedom is 1 minus the number of classes, 2 classes, parental and recombinant, so 1 degree of freedom. On an exam, you would be given the table of critical values. You're expected to look it up for your homework, but the critical value at the 5% significance level for 1 degree of freedom is 3.84. Our calculated value was a lot bigger than that, so we will reject our null hypothesis. Now, I'm not going to write this all out, but the genetic conclusion is that there is enough evidence at the 5% significance level to conclude that the color and leaf-shaped loci in peanuts do not assort independently. By rejecting independent assortment, this is evidence that the genes are linked. So now we can try to map those genes. One thing we want to do early on is determine the order of the genes. I'm just going to slide this down a bit so I have some scratch paper. I do this by writing both parental types. Well, we'll call these non-crossover since it's 3 genes, NCO types. And let's see, we had yellow, spreading round, and orange erect pointed. So those were my 2 non-crossovers. And then I write 1 double crossover. Does not matter which double crossover I pick. So our non-crossovers are the 2 pure breeding parents. So NCO and NCO. And I'm just going to get rid of these P's for now so that we have a little bit more writing space. They are the most common. Our double crossovers are the least common. So I want to write 1 double. It doesn't matter which. I'm just going to pick the top one, yellow spreading pointed. I look at what's in the non-crossover. Excuse me, I look at what's in the double crossover. I circle it in the non-crossover. Yellow, spreading, pointed. When you do this, go to the non-crossover that only has one thing circled. That is in the center. So our pointed round locus is in the center. And I can put those on our map. Let's see. It doesn't matter which we put on top and which we put on the bottom, but we need to write 1 non-crossover on top and 1 non-crossover on the bottom. So with pointed, I have orange and erect. And that's 1 non-crossover across the top. There we go. And the other non-crossover was yellow spreading round. So with round, I'll have yellow spreading. Our next step, I'm bringing another copy down here. Our next step is to classify these others. We've already classified the non-crossovers and the doubles. Non-crossovers most frequent, doubles least frequent. Non-crossovers exactly like our pure breeding parents. And so that's always the thing you need to look at. Wonder how to get rid of that. There we go. So let's see. Orange, cross in region 1, round, stay down, spreading. So orange spreading round, that's going to be an SC1. The other one starts at the bottom, yellow, cross up in region 1, pointed, erect. Yellow, erect, pointed. That's also an SC1. For the double crossovers, orange, stay up, pointed, cross down spreading. So orange pointed spreading, orange pointed spreading, that's an SC2. And yellow, stay down, round, cross up, erect, yellow, round, erect. That's an SC2. So we have to classify all of our progeny types, and then we can calculate the map distances. Again, I need a little bit of scrap paper, so I'm going to pull it up here. Our map distance for region 1 is the SC1s plus the doubles divided by the total, all that times 100. So I've got 85. Oops, nope, I've got 102 SC1s. 102 plus 119 plus 11 plus 7 divided by my total of 1,308, all that multiplied times 100. And that comes out to 18.27. For region 2, I've got SC2s plus doubles. Multiply times 100. The multiplying times 100 puts it into percentage units because remember, the map distance is the percent of crossing over. Just this part without the multiplying times 100 is the frequency of crossing over. Now I have my 85. And the other SC2 is 73. Still the doubles of 11 and 7. Still the same total of 1308. And we multiply that times 100, and it comes out to be 13.46. So I can put these on the map, 18.27 centimorgans and 13.46 centimorgans. Go. There's one more part to this problem. We want to calculate the coefficient of coincidence and the interference. The coefficient of coincidence and interference give us an idea as to whether or not a crossover in region 1 affects the probability of getting a crossover in region 2. And we do that by determining whether or not there's independence in the crossover between those two regions. Remember, if two things are independent, the probability of them both occurring is just the product of the individual probabilities. So, coefficient of coincidence observed DCO over DCO expected if independent. And here I'm talking about independence of crossing over between region 1 and region 2. Observed DCO, that's a piece of cake. 7 and 11. You've already labeled those. Expected DCO. Well, remember, this map distance means that there is a probability of 0.1827 of getting a crossover in this region, since 18.27% of the time we have a crossover here. There's a probability of 0.1346 of getting across in the second region. Remember, if two things are independent, the probability that they occur at the same time is the product of their individual probabilities. So 0.1827 times 0.1346 is the probability of getting a double crossover. But we need apples and apples. We have numbers of double crossovers in the numerator, so we need numbers of double crossovers in the denominator. We observed 1308 progeny, so we have the probability of a cross in region 1 times the probability of a cross in region 2 times our total number of progeny, and this gives us the expected number of double crossovers, assuming we had independence. And when we crank all that out, it comes out to 0.56, 0.56. Pretty far away from 1. We would expect this to be 1 if crossing over was independent between those two regions. The interference is 1 minus the coefficient of coincidence, so 1 minus 0.56 is 0.44. So we got 44% of the time, we got interference between crossing over in those regions. There's a lot to this problem. I encourage you to go back and work every example you can find. There are some in the practice problems. There's some, of course, in your homework, some in the lectures, the worksheets. Work every one you can find and get to the point you can do these in a closed book manner for the test. All right, I think we have one more page of this worksheet. Let's see. This is a reverse mapping problem. And here we're starting with the map and we're predicting frequencies of various progeny types. We are given the map, and look at this map. It's got 4 genes. Oh my, we haven't had that before. No problem. We're only going to look at genes that are adjacent to each other. There are lots and lots of genes along the length of a chromosome. So here we have lions. Golden is dominant to brown, roaring dominant to mewing, aggressive dominant to passive, and long mane dominant to short mane. Roaring passive lions with golden coats and long manes. That's one of our purebreds. That's really important. We're mated to purebreeding mewing aggressive lions with brown coats and short manes. That's our other purebred. So what we need to do is write one purebred across the top and one across the bottom. So we need to get them in order. So coat color, golden. Sound, roaring. Disposition, passive. And mane, long. Which means we have the opposite types for the other one. Let's see, brown coat. Mewing. Disposition, aggressive. That sounds like a lion. Maybe not. Haven't met too many lions. And short manes. There we go. Okay, so that's setting the problem up. Now we need to think about how to calculate these different things. Golden and mewing. Golden and mewing requires a cross in that first region. The map distance here is 0.12. Half of the individuals that cross in this region are golden mewing. The other half are brown and roaring. So we'll take half of 0.12. Oops. So we expect a proportion of 0.06 or 6%. Be careful if Moodle asks for a percentage, give them the percentage. If they ask for a proportion, give them the proportion. Here we're looking at proportions, so it's 0.06. Had this been a percentage, it would have been 6%. Aggressive, long. Here we need a cross in this last region. So half of those will be aggressive long, half passive short, 1/2. The map distance is 5 centimorgans, so our probability of a cross is 0.05. And when I multiply that out, I get, there we go, 0.025. And the last one, roaring and passive. I don't want to cross here. The probability of a cross is 0.19. So 1 minus 0.19 is going to be the probability of no cross. And again, we'll take half of that. And when I do the math here, we have 0.40. Okay. So I'm going to need to make something with map on it quickly. Done. I have the scissors. Scissors would be nice to have in a desk. Scissors. Trying to bring the map down so we can see it when we look at the bottom of the page here. There we go. Now we can see the map and the last part of the problem. Here we're asked to rank the progeny types from 1 to 5 based on our map and the various regions that we have on that map. So we need to decide where crossing over occurs, if it occurs a lot because it's a big region or not very much because it's a small region. Always, no crossover is more common than one. One crossover in a big region is more common than two. Yeah, and then two crossovers would be more common than three because I have three different regions here, so I could get a triple cross. So let's look and see where each of these cross. Brown, mewing, aggressive, long. One cross and in smallest region. Okay. Brown, roaring, passive, short. Two crosses. Golden, roaring, passive, long. No cross. That's going to be the most common. We'll just give them a 1 right now. Golden, roaring, aggressive, short. One cross in the biggest region. Golden, mewing, passive, short. Whoa, 3 crosses. Okay, no crossover, most common. One crossover will be the second most common class, with a cross in the big region being more common than a cross in the small region. Two crosses would be more common than 3 crosses. There we go. Well, I hope that you have learned something from this, and I hope this will encourage you to go back and practice similar problems on your own. Thank you for your attention. I hope you have a wonderful day.